All right, hello and welcome. Today's March 18th, Wednesday. It's supposed to be a short day. My goal is to hopefully shorten our casts, our streams. We're going kind of over the 1 hour limit. And of course, we want to make sure that we maximize our efficiency so that we do the most amount of things in the least amount of time, right? And yeah, definitely getting distracted does slow us down, which lengthens the stream. So let's try our best. We want to be a little bit more focused. Permaban. See, this is what I mean. It's starting. This is how it happens. All right. We have less viewers than usual. Hopefully, you guys are still keeping up with your schedule. It is very important that we don't just shut down. We continue with our normal schedule. You should treat all of your weekdays, your business days, like business as usual, and that you want to wake up at the proper time so that your sleep cycles are not messed up. Indoor exercising, I suppose, is also great. Literally did over 5 hours of homework yesterday, including the stream. Yikes. So let's get started. Let's make this shorter than yesterday. The first thing I want to point out is actually a typo that I made. I wrote, I didn't spell permeability correctly. I forgot the L and the I, so make sure you add that on. Permeability. I made sure to make a note of that in the comments in YouTube or the description. But anyway, it's permeability, not permeability. Good morning, AP1 student. Welcome. So yeah, do your chapter summaries, etc. So today we're going to go over some heavy-duty equations and some other concepts. This will get us going in doing our mastering physics eventually. But for now, you should definitely be almost finished with your summaries. You should be, ideally you're finished with your summaries already. Since it seems like you guys have less work to do overall from your other classes, without saying anything else, you should definitely have more time to do this stuff. No, not true. You have more stuff, more things to do. It's painful. All right. So what do we want to talk about today? Today, we'll start with where we left off. We were talking about how current carrying wires produced a magnetic field around it, and by looping it around many times, we could kind of amplify that magnetism, and it seemed to be purely based on the number of loops per length, the loop density, and of course the amount of current that is going through the wire itself, right? Let us begin with, wrong PowerPoint. Let me pull up the PowerPoint. Magnetism. We'll start with our PowerPoint right here. And we were, I suppose, we did our first right-hand rule number 1, which is the current carrying wire and the magnetic field around that current carrying wire. Only a volt thunderbolt? What? Imagine referring to something. First person plural is used in certain areas. Is that what you're talking about? I don't know what you're talking about. But anyway, here we have current carrying wire. We figured out that I feel like we are getting to see our teacher's true colors during this time. Okay, well, we can have these I don't know what you're talking about, but don't talk about other teachers. We can talk about this later, so let's focus on the physics first. Alright, so anyway, I'm losing my mind right now. You guys are really distracting me. Force on the wire depends on current I and L. Now, if I go to this slide here, are you guys seeing this? So if I have two wires, where are we? If I have two wires, here we are. Sorry, there's supposed to be a demo slide, but we can't do demos right now. So if I have two wires like this, each wire produces a magnetic field around it, based on what we found yesterday. Okay, and that magnetic field apparently applies a force onto the other current carrying wire, and based on its magnetic field. Essentially, both current carrying wires are producing their own magnetic fields, and the magnetic fields are actually applying forces on each other. So first, let us go back to our OneNote and define what is going on. It seems that using a uniform electric field, so imagine having that horseshoe magnet again. Okay. I'm going to draw it in 2D. Sorry, I guess never mind. I have to draw it in 3D. Dang it. Okay. Alright, so imagine this horseshoe magnet being on the XY plane. Would they like rotate around each other then if you put current in? So they apply forces, so we'll talk about that in a second. So imagine having a current carrying wire that is coming out in the positive z-axis. So we have y, x, and the positive z-axis. So our current is coming out this way. Okay, so this is a wire with current in it, and it's coming in the positive z-axis. Now, based on how I orient this uniform magnetic field, so imagine this being the north side, this being the south side, we know that on the outside, or the external side, outside of the magnet, it goes from north to south. On the inside, it goes south to north. So we have a nice uniform magnetic field here. Right? And so we use right-hand rule number 2, RHR number 2, which is for the force on a current carrying wire. Like so. All right, so the right-hand rule number 2, which is different from number 1. Now, number 1, you're wrapping around your fingers around your wire, and the curl tells you which way the magnetic field is. But here, we're going to keep our palm at 90 degrees, such that you have. Let's see if I can draw a hand. Here are my fingers. Here's slightly. Okay, and the hardest part is actually to draw the thumb. Oh, oops. Here we go. How do I draw this? Can we have Rebecca do this for us? Rebecca, help. I don't know what's wrong with my hand, but I think it's something like that. Is that what it looks like? Uh-oh, I have a 6th finger. That's not good. No, this is no bueno. Let's just stick to the PowerPoint, because I can't draw. The PowerPoint crashed. Oops. Cancel. Okay. PowerPoint. Okay. Boom. Oops. Dang it. I didn't want to show you that. Right hand rule, use your right hand, point your thumb in the direction of the current, point your other fingers in the direction of the magnetic field, and then your palm now points in the direction of the magnetic force. So this is the one. You thought it was beautiful? Alright, so let me bring it back then. Ryan Davis approves. Oops. Alright, so I is your thumb. Your fingers, whichever way, as long as they're pointing, 90 degrees to your thumb, is the magnetic field. So the reason why I do that is because you have, there we go. The reason why I do that is because you have multiple fingers, so they kind of represent the magnetic field lines themselves. So here's the magnetic field B. Yes. Remember, there's a 3-second delay, apparently, so sorry. So the magnetic field B points with your fingers, your thumb, which is 90 degrees to your fingers, is the current. And finally, your palm, which is in the Z-axis, I'll use circle with a dot. That means the palm is coming out of the page or out of the board. The palm, let's use a different color, blue. The palm represents the force. Green represents current. And the other one is the magnetic field. Okay, so let's go ahead and use the right-hand rule. And typically when you're taking a magnetism test, you're going to be doing this, people might laugh at you, but basically you're turning and twisting your right hand whichever which way and trying to figure out what the direction of the force is, etc. So, thank you for following. Nice. Make sure you follow so you can type in the chat. Yeah, it is a cross product. It is a cross product. Let's see. I cross into B. And we'll get to the equation in a second. Negative B cross I. Yeah, that is also true. It's not up. It's circle with a dot. That means it's in the positive Z-axis. So out of the page, out of the board. Okay, so you have 3 different axes, X, Y, Z. So I is in the positive, B being in the negative X, I guess, and then F would be outwards. All right, so let's do it here. Okay, so in order to do it, you have to first orient your, so just make sure your palm is 90 degrees, so it's flat. We call this the Buddhist palm technique. So if you ever palm someone as a martial arts move, keep your thumb and your fingers 90 degrees to each other, as well as your palm 90 degrees to both of them. Okay, align your fingers to the right. So align your fingers to the right. Your thumb should be pointing out of the page, so towards you. So now you have to kind of rotate your hands so that the thumb points towards you while your fingers point to the right. This will give you a force that is upwards. What was the color for force? It was blue. So we have a force that is upwards. Yeah. You got to get your yoga on, your stretches. So let's do some physics yoga. The entire state basically got promoted to next grade. They're in summer. Nice. My hand is curled and it's 360 degrees. Did I do it right? No, that is rule number 1, Ved. Rule number 1 is to find the magnetic field around a current carrying wire. So what is happening here essentially is that the current carrying wire is producing a magnetic field around it. So using our right hand rule number 1, we can see that there are these concentric circles that are looped around the current carrying wire. The current carrying wire has its own magnetic field. The magnet has its own magnetic field, the red lines, and therefore these two magnets, the current carrying wire and the magnet itself, are repelling each other in a way such that the wire itself lifts upwards, goes upwards. Okay, and of course if I reverse the direction of the current, so if I change the current is now going into the board. Magnetic field, let's use red. Magnetic field stays to the right. Okay. Shall we class load up? Let's class load up. Which way is the force? Actually, let's not class load up. This is too ISBO for us. Yay. Alright. Pull? Nah. So essentially, now you have to stick your thumb into the page while maintaining your fingers pointing to the right. So fingers pointing to the right while thumb sticking into the page, you'll see that your palm points downwards. So the force is down. I should use green. Oops. Green. Here's my legend. Yeah, your thumb is the current, the arrow itself, the direction of the current. It banned Jacob. He didn't say anything. Or, I mean, my moderator deleted it, whatever he was saying. So, unless you guys are also chatting in the group chat, don't. Ignore the group chat. Isn't current a circle with a dot here? No, this is example 2. Example 2. This is example 1. So now it should make more sense. Yes. You see, if you guys are chatting in the group chat, you're going to get lost. This is a follow-up. Basically, by reversing the direction, we basically also change the direction of the force, assuming that the magnetic field is the same. Okay. All right. So the equation is very simple. It's F Bill, or Bly. Now, Bill is good as long as everything is constant and at 90 degrees to each other. Only if B and I Jacob out here finessing the system. Only if B and I are perpendicular. Okay, but we need a general formula such that we can send our current in any direction. All right, you can use B sine theta, or you can do F is equal to L times I, which is the vector, cross B. Or Bill sine theta. Where theta is the angle between I and B. L is the length of the wire. It seems that the longer the wire, the more force. F is force, B is magnetic field. And of course I is current. Okay. Now magnetic fields, remember, are measured in Teslas, T, and one Tesla. 1 Tesla, yeah, 1 Tesla is 1 Newton per am meter. One Newton per am meter. What happened? Amps times meter. Not an ammeter, but amp times meter. No, not multimeter. Amp meter. Current times length. Yeah, well, Jacob is creating a hostile work environment already. Jacob, you didn't learn your lesson. Oh God. Well, I can't see your group chat, so I don't know what you guys are doing. Jacob is a hostile work environment. Ouch. All right. Anyway, so the force is, B times I times L. Now we can finally get back to our PowerPoint and make sense of what we're shown here. We're going to combine what we saw yesterday with what we have today, right? Okay, so the magnetic field around a wire is given by mu naught times I divided by 2 pi r or 2 pi d. Okay, based on how far away you are from your wire, you can find the magnetic field. Of course, it decreases, exponential decay, not negative slope. So B around a wire is equal to mu naught, the permeability of free space, divided by 2 pi r. Again, this is from a line integral, from basically a surface, not surface integral, but the closed loop line integral. So that's yeah, sure. This thing here. The physics, isn't it Newton times meters over amps? No. Just look at the formula. Force is BIL, right? So if I divide both sides by IL, I get B by itself, and so B is newtons over amps times meters. There you go. Dude, are you happy now? Boom, derived. Consider yourself derived. All right. So times the current. So this means that if I had a current carrying wire and I am radially this far away, r, we can figure out what the magnetic field strength is. And it's a circle, so any point along this circle that is around the wire at radius r will have the same value for its magnetic field. Okay. What's a wire? What happened? It's lagging? Is it? Oh yeah, it is lagging. Oh my gosh. I don't think Twitch can handle everyone being online at the same time. It's better. Okay. Yeah, I can see the big dip. Anyway, so mu naught times I divided by 2 pi r, the circumference of the circle you're making, basically. No, it's not. It's not based on how many people we have on our channel. Obviously, it's based on everyone that is logging on to Twitch because they have nothing else to do, so they're just playing games and stuff. Right? Ay, ay, ay. These kids, man. ISBO, come on now. The server strain isn't from one stream. The server strain is from all streams combined. Okay, so if you can take a look at the PowerPoint now. So what we have is the magnetic field from wire 1. So the magnetic field from wire 1 is based on current, and this is very important. So the magnetic field from wire 1 is based on the current in wire 1 divided by how far wire 2 is. And so wire 2 is d distance apart, therefore it is distance of d away. So it's wire 2 is going to experience the magnetic field from wire 1 based on that d distance. Okay? Therefore F2 being the force on wire 2. Oh, Mr. Z, I heard College Boarders. No, I don't know anything about it right now. We're just gonna have to wait. They don't tell us anything ahead of time. We're gonna have to find out at the same time. In any case, we're not doing this just for the AP test anymore. This is for us. You know, some of you want to eventually get into STEM. You know, you still have careers and other things to get into. So you're still going to need to learn this. All right. So F2, which is the force on wire number 2, is based on the magnetic field from wire number 1. So if you can take a look at this equation, first we write down the the force, so the B1, which is mu naught times the current in number 1 divided by how far wire 2 is, d, and therefore the force on number 2 should be times BIL, or Bly. So this magnetic field, mu naught times I1 over 2 pi d times current 2 times the length of wire 2. Does direction of current matter? Yes, I does matter. Okay, so L2, I2 times mu naught I over 2 pi d. When it comes to the formula, the direction of current does not matter. The formula is just a magnitude, right? You're just plugging in the values, and you're set. Now, based on this, we have various interactions, right? And I'm sure when you did your chapter summaries, you'll see if you have two wires that are carrying current in the same direction, up and up, what happens to them? Well, let's take a look. One wire at a time. So I'm going to move this to the side here. First, let's go and draw the magnetic field. Oh, undo. The magnetic field around this one. If I have my right-hand rule number 1, so one note, boom. Right-hand rule number 1, the curl goes around this way, which means circle with dots here and circle with X over here. Okay. And if I do it on the other one, thumb up, we see that on the left side it's still circle with a dot, and on the right side it's circle with an X. And one way I show students, or just to simplify this process, is that notice how in the middle you have opposite stuff. X's from one, circle with dots from the other. Therefore, they kind of attract each other, and the wires get pulled in towards each other. Okay. wires attracted. This is just a model that I'm using. It's just an easy way to figure it out. However, you don't have to do this way. This is just a shortcut. The correct way, I would say, would be to actually use right-hand rule number 2, on both wires. So let's go and use right-hand rule number 2 on both wires, starting with wire 2. Okay, we know that on the right side we have a bunch of X's from wire number 1. That's cool. Okay, so we're going to go ahead and use right-hand rule number 2 to find the force on this second wire. Okay, so remember the current is going up, so you have your finger pointing upwards. Stop, don't be mean. Let them learn. You want to propagate the wave of knowledge. We want to all resonate at the same frequency to make the vibration stronger. Let's all vibe together. There you go. Anyway, everyone with us? So we created a magnetic field based on the current carrying wire of number 1. This is wire number 1. And we're going to see what force we get on wire number 2. Since we have X's, we want our fingers to point into the board while the thumb points upwards. So now if you keep your Buddhist palm technique flat, your fingers go into the board while your thumb points upwards. Which way does your... No, did I say that wrong? Fingers pointing into the board, thumb pointing upwards. We are all resonating in Kumbaya. Yes, very good. How did you even do that? Oh, it's asking me to hold a message for a reason. Denied. And so your palm should be pointing left. Therefore, the force, I use blue for force, so let's stick with the same color. The force on wire number 2 is left. So this is F21, meaning the force on wire 2 by number 1. F21. Right? Bante. Thumb pointing up, fingers into the board. Look at your palm. Which way does it face? Give yourself a thumbs up while pointing your fingers straight. Make sure you keep your hand flat. You don't want to curl. This is right-hand rule number 2 for the force. All right. Now, let's go and do the same thing for the other wire. Do the same thing for the other wire. So I'm going to delete the magnetic field from the first wire. The first wire experiences the magnetic field created by the second wire. The magnetic field created by the second wire is circles on the left side. A circle with dots on the left side. So that means that wire number 1 is going to experience a magnetic field that comes out of the board, while everything on the right side of wire number 2 would have a magnetic field that goes in. Remember, it curls around. My thumb points down. What? Oh, are you using your left hand, Mark? If you're using your left hand will give you the wrong direction. We've had that happen before on quizzes. Alright, so this blue stuff is the magnetic field created by the wire on the right side, wire number 2. Yeah. So notice how the magnetic field to the left of wire 2 comes out of the board, and this is the field that wire number 1 is going to experience. Okay, so now let's go and try our right-hand rule number 2 again. Fingers pointing out of the board towards you, while your thumb is still upwards. This is kind of hard. You have to kind of curl your entire arm, not your fingers, curl your arm so that you can point your straight fingers towards you. And so the thumb is pointed upwards, and you'll see that your palm is now pointing to the right. Therefore, the force on wire number 1 due to wire number 2, F12, is the other way. User error. Yeah. User error. You know, when you write, as an engineer, when you write like SOPs and like instruction guides, you try to kind of, make it as easy as possible, step by step, that anyone can follow and, make whatever you're trying to sell, put it together again. And sure enough, there's always someone who just tries to follow and then, somehow attaches the door to their forehead or something. Yeah. Well, that's what we call user error. Yeah, it's not that the calculator gave you the wrong answer, it's that you punched in the wrong stuff. You're so bad that you can't put Legos together. Ah. What? Why would you do that? Is that Jacob? That must be Jacob. Let's ban Jacob. Alright, so as you can see, the two forces are towards each other, therefore it is attractive, and so they're going to come together. If you have current going in opposite directions, so one going down, one going up, this will repel. What? What is going on? Okay, so these two will repel. Alrighty then. Cool. So do we know units for mu naught? I don't think I gave you units for mu naught. Did I? Can anyone tell us what the units for mu naught is? See if you can use the equation to solve it. What are the simplest? Chat, what are the units for mu naught? Permeabilities, no. Meters, no. Okay, figure it out based on what equation I gave you yesterday. Or today, actually. Look at this. Look at the equation I just gave you. Very good, Mystery Wizard. Newtons per amp squared. Right? Just take a look at this. Right? You have I times I, which gives you amp squared. All right? Now you have a D in the denominator, which is meters. L, which is length, is also meters. And the meters cancel. So you have newtons over amp squared is what mu naught should be. No. Nishank already got it. Is Mystery Wizard Nishank? I'm going to assume it is. All right. Some people are saying it's too much. We're supposed to go over bios of art law today. Should we do that real quick? Yeah, let's go and do that. No, let's not do that. It's actually quite a lot. We'll start with bios of art law tomorrow. And then we'll take a look at where we got this mu naught b equation using some of Maxwell's equations. And then eventually we'll put together all four Maxwell equations. And then, those shirts that have Maxwell equations written on and people wear them to look smart. You will actually know what they mean, and not just act smart, but be smart. Yeah, it pays to take physics, of course. What is Bart Simpson law? I don't know. All right, I think this is all for today. Consider waiting till tomorrow to learn about Biot-Savart law. Finish your mastering physics so we're not all behind. I'll see you next time.